networks. In today's class 5 under GATE exam, we are going to deal a special theorem called maximum power transfer theorem under network theorems. Already, we have dealt with the basic concepts of maximum power transfer theorem in our previous classes. You can check back those videos and again come back to this class. If at all you are interested to know exactly the maximum power transfer theorem, right now we can go with the basic definition for DC network. Like when you have a DC voltage source, you have a resistor which are connected in series with the load, and the circuit is closed like this, where uh, it states that the maximum power can be transferred from source to the load when load resistance is equal to the source resistance. So current when flows to the load that is in series with source resistance, and that is also in series with source voltage. So this is applicable for this kind of network or circuit, what you call, when you need to apply the maximum power theorem for AC connected circuit, where you have source voltage given by Vs, but here the source voltage is sinusoidal in nature, and instead of resistors, we have here impedances, that is Zs and Zl. Since AC circuits contain the reactive power, that's why we replace resistors with impedances, where you have the resistor along with the reactive components, that is due to inductive nature or due to the capacitive nature. So Z is a combination of that. So for this kind of AC circuit, the maximum power transfer theorem is defined as maximum power can be transferred from source to the load when load impedance is equal to the complex conjugate of the source impedance. When we apply this concept to the AC and DC networks, we'll come to know what exactly maximum power transfer theorem states, or it gives the information about. So we'll see the first problem which was asked in GATE 2017. A basic analysis you're going to obtain by solving this circuit, which is shown in figure 1. This was asked for 2 marks under set 1. So the maximum power transfer to the resistor R is dash watts. So this is for 2 marks, no negative marks for this particular question. So in doing this, we'll find out the open circuit voltage across this resistor, and we'll find out the equivalent resistance across this resistor. First, we remove the resistor from the given figure, and we have to apply KVL. So you can see here I'm taking out this resistor, and I'm trying to find out the voltage across this terminal, because I need to obtain the terminals equivalent network and along with the load R here. So for that, we have removed this resistance from this particular terminals. So when you are going to apply KVL, what you're going to get, you're going to get the currents which are flowing in the given loops. So current 1 and current 2 would be in this fashion, clockwise, in assuming both the currents which are flowing in this fashion. When you apply KVL for the first two, we are going to get minus 5 plus 5i1, so it becomes a drop. Then you have directly from this point to this point 6 volts, negative sign on the left side, so that is why here it is minus 6, plus you have this 5 shared by these two loop currents i1 and i2, so i1 minus i2 equal to 0. This particular equation can be rearranged as 10i1 minus 5i2 is equal to 11, and this we are taking as equation 1. And from the given data or the circuit, you can easily estimate what exactly is the value of I2. I2 is nothing but 2 amperes. So these two equations are need to solve. Then you're going to get the value of I1, which will be equivalent to 2.1 amperes. Why? This I2 is there, that is 2. 2 multiplied with 5 becomes 10. And 10 when goes to the right hand side, it becomes 11 plus 10 becomes 21. So 21 divided by 10 will become the value as 2.1 ampere. So this is how we frame the value of I1. Now once the I1 is known, you can easily find out what exactly the voltage across this terminal. So what I'm going to do, I'm going to apply again KVL to this loop in this fashion, where you have minus 5 plus 5 I1, okay, that is a drop, and from this point to this point you have the voltage, that is VOC, and that is why we have framed here it as VOC equal to 0. Now from the equation 1 and equation 2, we have obtained the value of I1, that is 2.1. Just substitute the value over here, you're going to get the value of VOC, which is equivalent to 5 minus 5 multiplied with this 2.1. This will give you the value of voltage as minus 5.5 volts. Now once the value of voltage is obtained, try to find out the resistance across the same terminal. That is when you have removed the R, that terminal. So you have to short circuit the voltage sources. So I have shorted here the voltage sources. And if at all you have a current source, you have to open circuit it. So we have a current source of 2 amperes, that is open circuited. So figure 1b looks like this, and from this we need to find out RTH. In fact, when you look into the figure 1b properly, this short circuit wire replaces this resistance, and this open circuit wire can be easily removed. In fact, R terminals would be like this. So in fact, you have 5 parallel with 5. So R terminals will be equal to 5 into 5 by 5 plus 5, which is nothing but 2.5 ohms. Now once we obtain the value of resistor and voltage, you can easily find out the maximum power, which is formula is given by VOC square by 4 into RL. As I told you, you can check back to our previous videos where we have derived the condition for maximum power. From that, directly I am writing here the power equation, that is VOC square by 4 into RL. Now, the value of VOC is minus 5.5 square divided by 4 times multiplied with this 2.5 will give you the value as 3.025 watts. So this is the perfect answer. So you need to round it to 2 decimals. Then also the answer will be 3 only. So in fact the power here it is 3 watts. So it's a basic problem in power calculations for maximum condition. Like this we have some more numericals. Like in the next numerical you can see in figure 2 you have RL, that is variable in nature. You have source voltage and impedance value is given by 4 plus 3 J ohms. This was asked per gate 2013 for 1 mark. So a source voltage Vs of t is equal to V cos 100 pi t has an internal impedance of 4 plus 3 J ohms. If a purely resistive load is connected to this source, has to extract the maximum power out of this source, its value in ohms should be. So options given are here 3, 4, 5 and 7. So clearly here RL is to be obtained, and that RL should be matched with the magnitude component of this impedance. So for that, the maximum power will be transferred to the load when load resistance is equal to the source resistance. Since resistor is connected and you have impedance component here, so that impedance value I will change it to modulus value. So 4 plus 3j modulus value will be obtained as under root of 4 square plus 3 square, which is equal to 5 ohms. So 5 is the right answer. In the next problem, you can see, which was asked for gate 2003 for 2 marks. Figure 3 shows the figure where two AC sources feed a common variable resistive load. Again, here also the resistor is variable. Okay. Under maximum power transfer condition, the power absorbed by the load resistance RL is. So you need to obtain the Thevenin's equivalent model connected to the load resistance, and then you can calculate the value of RL. After calculating the RL, you can easily obtain the power value. For that, observe the figure carefully. You have 110 volts at 0 degrees angle and 90 at 0 degrees angle. Both are voltage sources. They are AC sources, and that too the value is given in the polar form. Whereas the impedance value is given in the rectangular form, that is 6, and you have J8 ohms. Again here you have 6 and J8 ohms. So how to solve this problem? First, I am going to apply KCL to the figure 3a as shown here. So we have removed RL from the given terminal. So RL is removed. Okay. Now VOC we need to find out here. You can apply mesh analysis or node analysis to get the value of VOC. Since in the previous problems we have seen the mesh analysis approach, now we are going to see the node analysis approach. So here I am going to assume the node as VOC, and that node is assumed to be at the dominating condition. So that node voltage minus 110 at an angle 0 divided by 6 plus J8. This becomes one branch current plus again you have this branch. On the other side you have this branch which is having 90 at an angle 0 degrees volts. So VOC minus 90 by 6 plus J8 equal to 0, thus satisfying the KCL for the given from the given circuit. So we are going to just take the like terms on one side and like terms on other side. So here you can see VOC by 6 plus 8J repeated twice. I am taking on the left hand side and it is equated to the constant values. There is 110 by 6 plus 8J and 90 by 6 plus 8J. So it's uh, easily you can simplify this equation to get the value of VAC. VOC is equal to 100 volts. How you got 100 volts? You see here you have 6 plus J, 6 plus 8J. So that can be easily removed. Then this multiplied with 2 becomes T 2 times of VOC and 110 plus 90 becomes 200. So 2 cancelling out 200 becomes 100. So that is the value of voltage what we obtained from figure 3a. Now let us obtain the value of RTH. So RTHs can be obtained by short circuiting the voltage sources. So on the both sides of the given figure 3, I have shorted the voltage sources and this is how the rest of the network would look like. So easily you can apply the value of RTH with the parallel combination of the formula and this value will leads to 3 plus 4J ohms. So we have done with VOC, we are done with RTH. Now I am drawing the Thevenin's equivalent circuit for the given circuit which is in figure 3 as figure 3C, where the voltage source is obtained as 100 volts and the impedance value is 3 plus 4J. Now easily you can get the value of RL. From the previous problem you can see RL is obtained as under root of 3 square plus 4 square. Why? The load resistance should be equal to the modulus of the source impedance. So that is why RL is equal to under root of 3 square plus 4 square. So this value is nothing but 5. Alright. Now 5 is the value of resistor and 3 is already there. So when you calculate the load current would be 100 by 8 plus 4J. How 8? 8 is 3 plus 5 becomes 8 plus 4J is the given impedance, given reactor component value. So I load in modulus form is nothing but 100 divided by under root of 8 square would be 64, 4 square would be 16. So 16 plus 64 gives the value as under root of 80. So I square load will be equivalent to 100 square divided by 80. Now once we are done with this, which is flowing in this figure 3C, you can easily calculate the power. Power formula is I square R L. So you are having the I load square value which is as 10,000 by 80 multiplied with RL. So this will give you the value as 625 watts. In the next problem, which was asking GATE 2014 under set 3 for 1 mark, it goes with the concept actually. A non-ideal voltage source Vs has an internal impedance of Zs, right? If a purely resistive load is to be chosen that the maximum power transferred to the load, its value must be 0. Option B is real part of Zs, option C is magnitude of Zs, and option D is complex conjugate of Zs. Now you tell me what could be the answer. Most of the students would be guessing the answer to be D. But actually the answer it should be, since it's a pure resistive load, the answer it would be magnitude of Zs. That is what we have done with the about 3 problems. You can see that's why we have solved these problems and then we come back to this particular question. So the answer here, the magnitude of Zs. Option C is the right answer. Yes, you need to be careful while answering the numericals when we are dealing with Thevenin's theorem and maximum power transfer theorem. Very interesting concept. So directly without any solution, we can directly get the answer as magnitude of Zs. In the next problem, which was asked for question 5 under GATE 2011 for 1 mark, in the circuit given below, so this is the circuit which is shown in figure 5, the value of resistance required for the transfer of maximum power to the load having a resistance of 3 ohms is. Now you tell me the right answer. What could be the answer? The options are 0, 3, 6 and infinity. You should be very careful in answering this problem. See, load resistance should match with the source resistance. And since the DC value is given, so what could be the source resistance that should match with the load resistance? You should get the value here as 3. RL and RS should be same value. So what should we do in order to get the 3? Any guesses? If at all I put the numerical values 3 or 6 in this, you won't get the matching answer for maximum power transfer. That is, the load resistance should be equal to the source resistance. That is the not option. So option B and C are obviously wrong. Option D cannot be. Infinity cannot be the option. But option A, when you put the resistance here, variable resistance value as 0, this resistor R becomes 0. And when this becomes 0, this becomes short wire. When this is shorted, 6 ohms is also shorted. In fact, you have 10 volts directly connected to 3. So in fact, here the load resistance and the source resistance is answer is obtained as 3 only by making R equivalent to 0. So option A will be the right answer. I hope you like this class under session of maximum power transfer theorem. Please subscribe to this channel and press the bell icon for the future notifications.